It is 1956, Los Alamos. The Cold War is escalating, and physics simulations for atomic weapon yields are hitting a massive computational wall. The early computers of this era face a strict limitation. They process instructions sequentially. The machine has to finish one exact command before it can start the next. Look at these magnetic tape reels. They are physical, mechanical, and slow. The processor is fast and hungry for data, but spends its time completely idle, waiting for tapes to physically spin into position. We call this the I/O wait death spiral. These hardware limitations evolved from a technical headache into a persistent threat to national security timelines. When you are modeling thermodynamics for the military, waiting on mechanical hardware means falling behind in a nuclear arms race. The military required a radical leap in raw throughput, and IBM proposed a solution, Project Stretch. They guaranteed the delivery of a machine that would run 100 times faster than anything currently in existence. But look at this mathematical deficit. Newly invented solid-state transistors only offered a 10-fold speed increase, leaving a massive, mathematically rigid gap to the 100 times requirement. IBM engineers realized raw clock speed couldn't reach the target. They had to abandon traditional processing rules entirely. Reaching the target required a redesign of how information moves through time and space inside the machine. Knowing they couldn't force the physical components to run any faster, the engineers designed an internal architectural workaround to bypass the physical limits of the hardware. The first innovation was the instruction pipeline. Instead of a start-to-finish queue, data processing became an assembly line. Internal stages overlap. While executing one instruction, it decodes a second, fetching a third. This is the birth of parallel processing. This architecture allowed for the high-speed data retrieval that modern systems use to scan billion-row tables without the system locking up. Their second breakthrough was the lookahead unit, a dedicated hardware mechanism built to anticipate the processor's data requirements. As you can see in this node representation, the system prefetches data from those slow memory banks. It places the information in a high-speed buffer right next to the processor, pulling it before the CPU formally issues the command. This anticipation logic is the direct ancestor of modern high-throughput index scans and buffer caches. When running a query to pull specific records, the underlying engine pulls upcoming pages into memory so the processor never sits idle. The engineers overcame physical memory lag by decoupling data retrieval from execution, ensuring information was staged and ready before the processor needed it. By 1961, the machine was complete. But when tested, Project Stretch only achieved a 30-fold speed increase. It failed to hit the military's 100 times mandate. IBM took a massive financial loss. As you look at these imposing iron cabinets, consider that the company was forced into a price slash, cutting the cost of each unit from $13.5 million down to $7.7 million. By strict commercial and accounting benchmarks, the most ambitious computer project in history was pulled from the market as a failure. Yet there is a distinct historical irony here. This commercial loss provided the core hardware logic for the future of computing. Look closely at the console switches on the IBM System 360. The logic engineered for stretch, pipelining, prefetching, and the standardized 8-bit byte formed the hardware core for this machine. The principles forged to solve Cold War atomic math currently run the logic inside your mobile device and sequence the transactions of global financial ledgers. Stretch missed its 100-fold performance target, yet it established the core hardware logic that defines every modern computing platform.